2212 Lab 4, and the purpose of this lab is to measure the strength of a magnetic field with relation to the distance of a bar magnet. And the models we use include a real-life model, which include meter sticks, a magnetometer, and a bar magnet, along with a computational model in GlowScript. And to begin our fundamental physics principles, we have Biot-Savart's law, which relates magnetic field to a current, and the formula is shown on screen. And then we also have the magnitude of a magnetic field of a dipole, which is also shown on screen. And then we have the distance dependence formula, which relates distance to magnetic field magnitude and is equal to k times r to the n. And for a brief preview of our results, we found the n for the distance formula to be -2.2396, and for the k for the distance formula, we found it to roughly be 1.71 times 10 to the -6, and our mu, we found it to be 8.55 a times m squared, and for our experimental off-field axis magnetic field magnitude, we found it to be roughly 57.7 microteslas. Our system is the bar magnet, and our surroundings include everything else. And the initial condition is really just the constant mu naught over 4 pi, which is equal to 10 to the -7. To begin our experiment, we oriented the phone in such a way that we try to get the magnetometer as aligned as closely as possible with Earth's magnetic field to have better readings. And from there, we measured the distance between the bar magnet and the magnetometer chip to get like the values that we were told to find in the document. And once we got that, we recorded the distances to get those values, along with like the magnitudes that we read off the phone inside an Excel spreadsheet. We did this for the on axis, which is shown on screen, and we also did this for the off axis, which is also shown on screen. Oh, and also right here we also in the graph we have our n, and we also have our k if like we just take the constant and then raise it to a power of e. And for coding, we have like our initial conditions, and then we begin by making a function for the magnetic field, which if you remember the second formula that I showed, which is the one for like the the magnitude of a magnetic field of a dipole, we put that inside of this function, and we use this function over here to find the on axis and off axis magnetic field magnitudes, in which case we begin by having our distance, then creating our vectors, and then after that here the bottom two, they find like the on axis magnetic fields, and here we have the perpendicular magnetic fields, which are really just the orthogonal magnetic fields. And then we also found the magnetic field 45 degrees from the axis, which is currently being shown on screen. And then here's the image that comes when we run the program, along with the readings for the coding part of this lab. And for similarities and differences, we found that the magnitudes are relatively the same, with like numbers that are reasonable for both real life and the coding part. And for errors, one of the main errors was that we didn't really know where the magnetometer chip was. We just assumed it was on the top left of the phone, and we may not have aligned ourselves or the chip with Earth's magnetic field, but we tried to as best as we could. And errors may have also stemmed from devices that had currents in them, or even the table itself may have had a current in them. And for assumptions, we assumed the bar magnet to be a magnetic dipole, And for the statements observed, we observed statements 1 and 4, but we did not observe statements 2 and 3. And what if we had not aligned the magnetometer with the Earth's magnetic field? Then our readings would have been messed up because the bar magnet and the Earth's magnetic fields would have superposed. And like, what if we had stuck two identical magnets together? Then our magnitude would basically double, but direction is the same.